Chemical bonds hold atoms together, but how tightly? Bond energy measures the strength of a chemical bond, while bond length measures the distance between bonded nuclei. These two properties share a fundamental inverse relationship. Shorter bonds are stronger, and longer bonds are weaker. Understanding this relationship is essential for predicting molecular stability, reactivity, and physical properties across all of chemistry, from organic synthesis to material science. Bond energy, also called bond enthalpy, is the amount of energy required to break 1 mole of a specific chemical bond in the gas phase. It is measured in kilojoules per mole. For diatomic molecules like hydrogen gas, the bond energy equals the bond dissociation energy. For polyatomic molecules, bond energy is the average of all bond dissociation energies for that bond type in various compounds. The higher the bond energy, the stronger and more stable the bond. Bond length is defined as the average distance between the nuclei of two bonded atoms in a molecule. It is typically measured in picometers or angstroms, where 1 angstrom equals 100 picometers. Bond lengths are determined experimentally using X-ray crystallography for solids and microwave spectroscopy for gases. The bond length between identical atoms equals twice the covalent radius of that element. Bond lengths are remarkably transferable, making them a reliable property for predicting molecular structure. Bond energy and bond length share a fundamental inverse relationship. As bond energy increases, bond length decreases, and vice versa. This relationship arises from the physics of chemical bonding. When two atoms approach each other, their nuclei repel while their electrons are attracted to both nuclei. The equilibrium bond length occurs where attractive and repulsive forces balance. A shorter bond means the atoms are pulled closer together with stronger attraction, requiring more energy to break. The Morse potential is a mathematical model that describes the energy of a chemical bond as a function of interatomic distance. It accurately represents the anharmonicity of real bonds. The depth of the potential well, d sub E, represents the bond dissociation energy. The equilibrium distance, r sub E, is the bond length at the bottom of the well. The width of the well is related to the force constant, which measures bond stiffness. This elegant equation captures the essential physics of chemical bonding. Bond order is one of the strongest determinants of both bond energy and bond length. As bond order increases, more electrons participate in bonding, pulling the nuclei closer together and creating a stronger attraction. A single bond is the longest and weakest. A double bond is shorter and stronger. A triple bond is the shortest and strongest among carbon-carbon bonds. This pattern holds across virtually all elements in the periodic table. The type of orbital hybridization significantly affects bond length and energy. Greater character in a hybrid orbital means the electron density is closer to the nucleus, creating shorter and stronger bonds. For carbon-hydrogen bonds, as S character increases from sp3 to sp2 to sp, the bond length decreases and bond energy increases. sp hybridized carbon in acetylene has 50% S character, producing the shortest and strongest carbon-hydrogen bond at 556 kilojoules per mole. Bond lengths follow predictable trends across the periodic table. As we move across a period from left to right, atomic radius decreases because the increasing nuclear charge pulls electrons closer, and bond lengths also decrease. Moving down a group, atomic radius increases as additional electron shells are added, so bond lengths increase. For example, carbon-fluorine bonds are much shorter than carbon-iodine bonds. These trends are essential for predicting molecular size and reactivity. Electronegativity differences between bonded atoms affect both bond energy and bond length. In ionic compounds, a greater electronegativity difference leads to stronger electrostatic attraction and higher lattice energy. Sodium chloride has a much higher lattice energy than sodium iodide because the electronegativity difference is larger. In covalent bonds, a high electronegativity difference creates a polar bond with partial charges, which can increase bond strength through additional electrostatic attraction. Resonance structures describe molecules where electron density is delocalized over multiple atoms. In such cases, bond lengths are equalized to intermediate values between single and double bonds. The classic example is benzene, where all 6 carbon-carbon bonds are identical at 140 picometers. This is exactly halfway between a carbon-carbon single bond at 154 and a carbon-carbon double bond at 134 picometers. This resonance stabilization significantly affects bond energies. Bond dissociation energy, or BDE, is the enthalpy change when a specific bond in a specific molecule is broken by homolysis, producing 2 radicals. This is distinct from the average bond energy, which averages multiple BDE values. For example, in water, breaking the first oxygen-hydrogen bond requires 497 kilojoules per mole, while breaking the second requires only 426. The average bond energy is 462 kilojoules per mole. BDE values depend on the molecular environment and radical stability. Steric strain can force bond lengths to extreme values. Stretching or compressing a carbon-carbon bond by just 5 picometers requires 2.8 to 3.5 kilojoules per mole. The longest known carbon-carbon single bonds reach 180.6 picometers in highly sterically hindered molecules. At the other extreme, the shortest carbon-carbon single bonds are about 147 picometers. Unusually long bonds are exceptionally weak and reactive, leading to fascinating chemistry. Bond energies are powerful tools for estimating reaction enthalpies when experimental data is unavailable. The enthalpy change of a reaction can be approximated by summing the bond energies of all bonds broken in the reactants and subtracting the bond energies of all bonds formed in the products. Bonds broken in the reactants require energy input, while bonds formed in the products release energy. A positive delta H indicates an endothermic reaction, while a negative delta H indicates an exothermic reaction. Understanding bond energies has profound practical applications. In biochemistry, vitamin E has a remarkably weak oxygen-hydrogen bond, allowing it to donate a hydrogen atom to neutralize free radicals. In atmospheric chemistry, the nitrogen triple bond explains why nitrogen gas is inert and why the Haber-Bosch process requires high temperatures and pressures. In polymer chemistry, the strong carbon-fluorine bonds in Teflon give it chemical inertness and thermal stability. These examples show how bond energy governs real-world chemistry. Test your knowledge with this question. What is the relationship between bond energy and bond length? Option A, they are directly proportional. Option B, they are inversely related. Shorter bonds are stronger. Option C, there is no relationship between them. Option D, longer bonds always have higher bond energy. Take a moment to think about your answer. Next question. Which carbon-carbon bond has the highest bond energy? Option A, carbon-carbon single bond in ethane. Option B, carbon-carbon double bond in ethylene. Option C, carbon-carbon triple bond in acetylene. Option D, the benzene resonance bond. Consider what you know about bond order. Question 3. What happens to the carbon-hydrogen bond length as S character increases from sp3 to sp3 to sp? Option A. Bond length increases. Option B. Bond length stays the same. Option C. Bond length decreases. Option D. Bond length doubles. Think about how orbital shape affects bonding. Question 4. In benzene, what is the length of each carbon-carbon bond? Option A. 154 picometers, same as a single bond. Option B. 134 picometers, same as a double bond. Option C. 140 picometers, intermediate between single and double. Option D. 120 picometers, same as a triple bond. Remember what resonance does to bond length. Question 5. Which mathematical model describes bond energy as a function of interatomic distance? Option A. The Born-Haber cycle. Option B. The Morse potential. Option C. The Boltzmann distribution. Option D. The Van't Hoff equation. Think about which model involves an energy well curve. Let's work through a problem together. The carbon-hydrogen bond dissociation energies for methane, ethane, propane, and benzene vary significantly. We need to explain this trend in terms of bond energy and radical stability. First, identify all four carbon-hydrogen BDE values. Methane has 439 kilojoules per mole. Benzene has 473 due to the S-character effect. The tertiary carbon-hydrogen bond in isobutane has only 404 kilojoules per mole because the resulting tertiary radical is most stable. Secondary carbon-hydrogen bonds fall in between at 414. In conclusion, tertiary carbon-hydrogen bonds are weakest because the resulting tertiary radical is most stable, while vinyl and phenyl carbon-hydrogen bonds are strongest due to greater S-character. Problem 2. Estimating reaction enthalpy using bond energies. We need to calculate the enthalpy change for the hydrogenation of ethylene to ethane. First, identify the bonds broken. One carbon-carbon double bond and one hydrogen-hydrogen bond. The total energy input is 710 plus 436, which equals 1,146 kilojoules per mole. Next, identify the bonds formed, one carbon-carbon single bond and two carbon-hydrogen bonds. The total energy released is 347 plus 2 times 413, which equals 1,173. Finally, delta H equals bonds broken minus bonds formed, giving negative 27 kilojoules per mole. The reaction is exothermic, consistent with experimental values. Problem 3. Predicting bond length from bond order. The nitrogen-oxygen bond lengths in nitrite, nitrate, and nitrogen dioxide are different. We need to explain these values using bond order and resonance. First, nitrogen dioxide has a bond order of approximately 1.5 and a bond length of 120 picometers. Nitrite has resonance giving a bond order of about 1.33 and a bond length of 124. Nitrate also has resonance with bond order 1.33 and a bond length of 125 picometers. All three show intermediate values resulting from electron delocalization. The conclusion is that resonance equalizes and lengthens bonds compared to pure double bonds. Problem 4. Estimating bond dissociation energy from hybridization. The carbon-hydrogen BDE varies with hybridization. We need to calculate the increase per 10% of S character. Going from sp3 to sp2, S character increases by 8.3% and BDE increases by 25 kilojoules per mole. Going from sp2 to sp, S character increases by 16.7% and BDE increases by 92 kilojoules per mole. Normalizing these values, each 10% increase in S character strengthens the bond by approximately 39 kilojoules per mole. This is due to tighter electron confinement near the carbon nucleus. Problem 5. Comparing bond strengths across the periodic table. The hydrogen-halogen bond energies decrease from fluorine to iodine. Let's explain this using atomic size. First, atomic radii increase down group 17. Fluorine is the smallest at 71 picometers, while iodine is the largest at 133. As a result, hydrogen-fluorine bond length is only 92 picometers, while hydrogen-iodine is 161. This confirms the inverse relationship. Longer bonds are weaker. Hydrogen-fluorine at 569 kilojoules per mole is nearly twice as strong as hydrogen-iodine at 298. Fluorine is smallest, giving the shortest bond and the strongest bond. Let's review the key concepts. The inverse relationship between bond energy and bond length is the most fundamental principle in chemical bonding. Bond order directly affects both properties. Higher bond order means shorter and stronger bonds. Hybridization and character also modulate bond properties significantly, with greater character producing shorter and stronger bonds. Periodic trends in bond length follow the same pattern as atomic radius. Resonance delocalization equalizes bond lengths to intermediate values. The Morse potential provides the mathematical foundation for the energy-distance relationship. Finally, bond dissociation energy is specific to a particular bond, while bond energy is an average over multiple species. These concepts together form a comprehensive framework for understanding chemical bonding. The relationship between bond energy and bond length is one of the most elegant and practical concepts in chemistry. It unifies our understanding of molecular structure, reactivity, and stability under a single framework. From predicting reaction enthalpies to explaining why diamond is the hardest natural material, from understanding DNA base pairing to designing stronger polymers, these relationships are indispensable tools. The Morse potential provides the mathematical foundation, while bond order, hybridization, electronegativity, and resonance all modulate the fundamental inverse relationship in predictable ways. Mastering these concepts opens the door to understanding chemical reactivity at the